Jefferson Lab, and it doesn't really give you much of an idea what's going on here, but what it has to do with is nuclear physics and trying to understand how nuclei are arranged, how they operate, and how they, and also perhaps even explore some fundamental physics associated in the nucleus. So we'll talk a little bit about that. Before I go on to the remainder of this introduction, I thought I would invite any faculty member that is interested in going to dinner tonight. Zhang is going to be taking Professor Cole out to dinner after the colloquium, but if you're interested in going and joining, or maybe even a graduate student, you could certainly join if you have an interest in some of the things that are going on. Please hang out after the colloquium and see Dr. Zhang, and please join Dr. Cole for dinner. Dr. Cole received his bachelor's degree in 1983 from Cornell University in Ithaca, New York, and then went to Purdue University and completed his PhD in 1991 working at Fermilab at the Tevatron with Andrew Hirsch and Rolf Scharenberg.
Yeah, Scharenberg.
Yeah. And then later on, after that, he went to George Washington University and did experimental nuclear physics as a postdoc. He spent some time from 97 to 2004 at UTEP, University of Texas, El Paso, and then he spent a year as a sabbatical professor at Jefferson Lab in Virginia before taking a position at Idaho State University. So, you know, one of the things about the internet, it's very dangerous, is that you can look all sorts of things up here. And people's CVs are published and things like that. So some of the interesting things about Professor Cole, he's done some outreach activities with respect to nuclear physics and applications to Latin America. And I thought it would actually give a little bit of a perspective on that. So this stuff isn't just academic. There's actually medical applications associated with a lot of the techniques that are used for nuclear physics. And he has been exploring different isotopes that could be actually used for medical applications. We had a nice chat about that earlier today. The other thing that Professor Cole and I have in common is that at one point we were both chairs of the Academic Senate. Although his experience was a little better than mine. I resigned after 1 week. I knew what I was doing, right? But Professor Cole saw some pretty tough times at Idaho State. There's a lot of disputes still going on with the upper administration. So I just printed out this thing up from the Chronicle Higher Ed. A report denounces suspension of Idaho State University Faculty Senate. So at one point, they got in such a dispute that the president actually disbanded the Faculty Senate. And then that's when you were president. Then they reformed it again with him as temporary president. Then they suspended it again. So for some reason, they just wanted to get you out of your job. So there's some nice quotes in here, but I thought the most interesting thing was the last one, which showed up as says Courthouse News Service. I guess it's from Idaho. And it said, Idaho profs say university muzzles them. So I thought that was an interesting title. But what's relevant here is I think the physics department can learn a lot from Iowa State. Now there was a big complaint about a month ago about way too many emails going back and forth. Somebody would send an email and somebody else would send 2 emails to that. And at some point it got crazy. All the faculty were just getting way too many emails. And so this article, it says, Cole says that the Faculty Senate Vice Chairman was unable to send an email to faculty members about an upcoming vote for a proposal from the Constitution. Cole says he mailed the Vice President for Academic Affairs to seek permission to send an email to faculty about voting for procedure. He said that the Senior Vice President never responded by email, so he had to ask her in person. So I thought that was interesting because he didn't actually have permission to send the email to the Senior Vice President apparently either. So if we ask for permission of the chair or somebody each time before we send out an email, we could solve all of our problems. We have a question about how you actually send that email to ask for the permission. So it's kind of interesting. Anyway, welcome to the department, and
Thank you.
Had a nice visit, and look forward to your talk.
Well, it's been. I guess your past does follow you, but I'm not a politician anymore. I'm just a professor of physics. And so today I'm going to, and thank you very much for inviting me. I've had a wonderful tour of the facilities, and it's a very impressive university you have here. And so I'm going to talk about, as you can see the title right here, baryon resonances and the fundamental properties. And so basically this is a picture of quarks going around. There's 3 of them, and that's a very simplistic model. And then phasing in and out are quark-antiquark pairs. And so it's a very busy environment. I'm going to talk about what happens at the scale inside of a proton or a neutron. And so here's the slide that's saying that, well, the human hair, that's about 100 microns thick, depending, some 30 microns to 100 microns. You go down to a scale of a nucleus, which is 10 to the minus 15 meters, or excuse me, 5 times 10 to the minus 15 meters. Then you go down by a factor of, they say 10 here, but the proton's approximately about 1/8 of a Fermi. Okay, there's still some dispute on that. There's a lot of research on that, where there's 0.84, 0.88 Fermis, but on that order. And then you have a fundamental particle, up-down quark, and that's standard material that's inside this. And here is Rutherford, the one.
How do you define the diameter?
Oh yeah, that's a complicated because there's charge distributions, and so where the slope is changing the most. Yeah, but the issue is, and I'm just saying that there is laser spectroscopy with muonic atoms, and they show that it's consistent with 0.84 Fermis, and all the scattering experiments showed them to be 8.88 Fermis, and so, there's discussion on that right now, big discussion. And so protons are everywhere. As you know, the sun is made mostly of hydrogen, stars, and atomic nuclei. And so the mass is 938 MeV over c squared. Usually it's called about 1 GeV as a scale, or in American slang, at Jefferson Lab we say 1 JeV. I don't know if you've heard that before, but it's usually called 1 JeV. Yeah. And so charge 1 and spin 1/2. And so just what is a proton? Well, they were thought to be point-like particles, and then there were found neutrons were thought to be point-like particles, and with the advent of more powerful accelerators, they were found to have structure inside, and wrong one. So in 1955, Hofstadter measured the charge radius of proton, found that to be about 0.8 Fermi, okay, and he got a Nobel Prize for that in '61. Gell-Mann and Zweig postulated there were 3 quarks in a proton. Gell-Mann got the Nobel Prize, Zweig did not. And Friedman, Kendall, and Taylor found quarks in the proton. This was the partons. They did scattering, and they found out that it did not follow a 1 over sine to the 4th theta over 2 distribution. And so there was something in there that was ricocheting the innards, which were called partons. They got the Nobel Prize for this. And then Gross, Pulitzer, and Wilczek found that the mass is not just due to the quarks, but there's a thing called asymptotic freedom, and that has to do with the gluonic field cloaking the various quarks. And so as we go further and further in studies, we find out that the quark is a composite, complicated object. And so I'm going to talk about ways we look at this. Now, baryons are made mostly of, I'm not going to talk about dark matter, but most of the mass in the universe is made of protons and neutrons. And the 3-quark system, notice the colors, blue, green, and red, is the foundation of the development of the naive quark model. This is called quantum chromodynamics as opposed to quantum electrodynamics. It has to do with color. Quark-antiquark pairs manifest themselves within baryons. And the study of excited baryons is necessary to fully understand what makes a proton, and it behooves us to do this. And so this is my big introduction, why we do this, before we get into the details. Now, Nathan Isger was the chief scientist at Jefferson Lab until 2001. He died in 2001. But he was a great scientist, and he said something, and I like the way he said this, because in 2000, he said, why is this important? Why would anybody study this? And Nathan Isger said, well, the first thing is that nucleons are the stuff of what the world is made. Okay, so makes sense. We want to study what the world is made out of. 2, his second reason is that they're the simplest system in which the quintessentially non-abelian character of QCD is manifest. That might be kind of, I'm going to show what that means in terms of Lie algebras and such. I'm going to talk a little bit about Lie algebras. But it's non-abelian, and so there's a group theory behind that. And you can make simple predictions on naive models on what type of resonances you should have. The third reason is that history has taught us that while relatively simple, baryons are sufficiently complex to reveal physics hidden from us in the mesons. Let me remind you that mesons are quark-antiquark pairs. They may resonate and have spin, but quark hadrons are made out of more complicated stuff, 3 quarks, in a very naive, simple model. So I'm going to try to understand what makes a proton a proton. And so here is, in a picture, you see this big bump right here. That's called the delta. And then you see some other bumps. And so basically I take a pion onto a proton, I make something right here. And then you see some bumps here. Now, in my field, we dismiss people who are very naive as bumptologists or bump hunting, okay? Because if you do bumptology, basically you're forgetting all this stuff. And so what you have in here, if I draw a cartoon, but you see all these different spectroscopic states. So there's a bunch of stuff inside. So this is the mass of a proton right here, about 1 GeV. This is 1.2 GeV. This is a delta, 1232. Pretty broad, as you can see. It's about 200 MeV wide. And then you see a few other bumps. But hidden inside this is a lot of other stuff. And so we want to find this other stuff. And we have to use very specific, precise tools in order to uncover this other stuff. And so here's a very fanciful scientific diagram of this other stuff. Okay, this is from the time when I actually drew things on graphs, and I cut this and pasted this. And so what we want to do is we want to look in the range. Root S is just the mass, and that's 1.5 to 2.0 GeV. So in that range, just about 1.5 to 2 times the mass of the proton in that range.
So what is this energy? This is the energy with the collision?
This is the energy that goes into this thing, and that's the resonance energy. So that's the energy of the system.
Mass energy?
Yeah, and so, yeah. So I'm going to go through this, but I'm going to use a photon beam onto something. It's going to cause this to become more massive by exciting the substructure, and then it decays. Okay, and that's a resonance. And so I'm just trying to understand a very excited state of a proton. A baryon resonance is just an excited, heavy state of a proton. And so what we can do is we can say, well, they're all closely packed in this cartoon. They're on top of one another. They have broad widths, about 150 MeV. Now, let me remind you that the mass of a proton is 1 GeV, approximately, and 150 MeV is 15% that. So it's very broad on this scale. And what we want to do is we want to find the masses, the widths, the spin parity, which labels it, and the type of stuff it decays into, and the decay angular distributions of the stuff it decays into. With this information, we can identify what's inside. And so we have right here spin observables, so I'm going to talk about using polarized stuff in order to extract this information, because it's very complicated, it's very messy. I have to use very precise tools in order to access this information. So here's a quark, very, very nice picture, not drawn by me. Here's this picture again. And so a proton with 2 valence up quarks and 1 down quark, okay? And I have a virtual quark-antiquark pairs being continuously created and annihilated in this picture. So it's, just to give you an idea, and this is a very simplistic model. There's actually more going on, but this is just a start. And this brings us up to, let's say, about 1968, 1970, in terms of modeling this stuff. And so what I was saying is quarks have spin parity, and so I have 3 types of quarks. Let's say I have up, down, and one that's very close in mass is called strange. Okay, have you heard that? Up, down, strange. And then there's bottom, charm, and top. Okay, those are so heavy we're not going to see that. The top is about as heavy as a proton. Okay, and that's recently discovered. You have a question?
Well, I was looking at that picture and I was kind of wondering, the picture in the last slide. I was kind of wondering, what if one of those quarks came close, what if one of the real quarks came close enough to interact with that quark-antiquark?
That's a good question. There'd be gluonic exchanges and such, and so I have a lot more. I'm going to show pictures of actually gluonic fields inside and how we look at the nature of the quark in the asymptotic freedom limit and show that the nature of the coupling force between the quark depends upon how close you look at it. Okay, so I'm going to get into that. That's a very good question. And so I have 3 quarks, and then if I have a model here with this decuplet right here, the octuplet, if I presume there are 3 strange quarks, then I can predict the omega minus, and that's been seen. Okay, and so this model has had predictive power, just saying, you know, it's made out of quarks, and I add them in a certain way, which is called a Lie algebra. And so I don't want to really go into this too much, but I got to say something about this. Okay, so I said non-abelian, or Nathan Isger said non-abelian nature of quarks. What he was saying is that he can use a Lie algebra for this. What it says is that I have an SU6 supersymmetric unitary 6, which is basically of up-down strange quark, and then quarks come in two different types. They have spin degrees of freedom. Spin up, spin down is the language usually, but it's not really spin up and spin down, it's just two different states. And so if I do this for 3 different quarks, I have a 6 by 6 by 6 Lie algebra. And this can be broken down if you do the necessary mathematics and into a 20 plet, a 70 plet, a 70 plet, and a 56 plet. And so I have structure. And so I look, I'm not going to go through the mathematics of this, but I have a structure, and I can look at this structure and see if it fits according to this very simple Lie algebra. This is a very naive model at this time. And then I also have angular momentum states, which is basically an orthogonal matrix that has 3 states. So it's very complex. I mean, it's rich. And so if I do this for symmetric, I can have these boxes here, and they basically say, okay, proton is well known. That's a 56 plet in this language. It's well known. Green means 4 stars. It's been seen. We've seen a proton. The delta 1232 is well known. That's right here. Okay, and then we have other things with green, meaning it's got 4-star rating, like the hotel group. You know, Michelin star rating to hotels. This is the PDG star rating for baryon resonances. And these, you see, I have some boxes that say, well, I see this quite well. Maybe I see it. Kind of, sort of, I see it. I don't see it. So we have a whole host of stuff according to this model using Lie algebras that says it gives me a mechanism to look for stuff, and yet I have this conundrum. And the conundrum is I have missing baryon resonances. So is this naive model, as I keep on saying, of Lie algebras the right way to approach it? Perhaps, but we have to go further.
What are the dimensions on that diagram?
This right here is just the angular momentum, and this is the spin state. Basically, what I'm doing here is I'm kind of looking at, let's go back a little bit. I'm going across this way and looking at these various spectroscopic states. Okay, that's what I'm trying to do. And it's kind of a funny way of displaying it, but this is what I'm trying to access these different states. And so the thing is, there may be 2 models here. There may be diquark models, and so it says somehow, maybe I have 3 quarks and somehow they're bound pairwise. Okay, and then I have a 3rd one out there. That's a possibility. There's no reason why I can't say that, although it seems very strange to be bound pairwise. And not all states have been found. Now, perhaps I've not seen all the modes. I've not had detectors that can measure everything that comes out. So I have a photon coming in, some resonance state, and stuff comes out. Different particles come out. If it's a multi-state particle, I can't, 3 pions or whatever. It's very hard to see that unless I have a very big detector that can measure all of phase space. Okay, I use photons here because photons are adhere to quantum electrodynamics. They don't see the strong force. So remember, the strong force is that which binds protons and neutrons together or makes up the quarks inside of a proton. And so when I have an outside thing coming in to measure it, it doesn't see the strong force. It only sees the electric force. Okay? And also, I can have excitations of the spinning, twirling, whirling about. I can have breathing modes. I can have lots of stuff. That's what I'm saying. This is messy, messy stuff. Now, what I have here is, this is a little thing, but I put this together several years ago in a proposal. And what I did is I said, okay, here are the states right here that I would like to look for, and notice some of them don't have stars. I just look on this part right here. Forget about that part. That's a delta. I just want to talk about this right here. And so I have a photon coming in with a neutron. It makes some intermediate states, so it causes the quarks to do something, okay, some sort of excitation, and then it decays. And that L talks about the relative angular momentum between the meson it decays and neutron. Now I look at this and I say, okay, some of them have boxes here. These boxes, these are the, the different plets right here. That's the Lie algebra. It's just labeling this. But the boxes mean it's consistent with the diquark model. Those unboxed ones are not consistent with the diquark model. So there might be something here. So this is interesting right here. And these are interesting. These have been seen. So we look at this bumpology right here, and we have stuff in here. And then I could say, well, I have either diquark or spherically symmetric quarks, okay? So the big question right here is, I want to identify these things with a precise tool so that I can simply answer the question, or ask the question and answer it, is it consistent with this type of symmetry or this type of symmetry inside? And that's a very simple question. And it turns out that question's a little too simple, but it's a start. And so what I'm going to do is I'm going to say a few words on photoproduction. And so I have a photon coming in here, and a photon can do a weird thing. Photons can have a strong component. Photons can become quark-antiquark pairs. Okay, so it can act like a virtual quark-antiquark pair, scatter off the proton by a pion exchange and become an omega meson. Or it can come in like this, become an excited state, and decay by omega meson. How do I determine these two, or differentiate between these two? That's not a question. That's basically a rhetorical question. I'm going to show you how I differentiate between these two behaviors. As you can understand, this is very different from this. This is exciting the stuff, and this is scattering. And so I'm going to use a fixed frame. I'm going to use right here, and I'll show you in just a minute. Now, I'm going to talk a little bit about Jefferson Lab. Jefferson Lab has, and I'll show where this is, but we want to find out the goal of Jefferson Lab is to understand the structure of quark, how protons and such, let's see, investigate the nucleus of atoms at the quark-gluon level. So inside I have little quarks right here. I have gluons, combining them. I want to understand how quarks and gluons make up protons and neutrons. That's one of the big things. The next thing, what causes the nuclear force? What makes protons and neutrons bind together? Why are protons and neutrons different? Okay, these are fundamental questions. What is the structure of nucleons when they're on top of one another? Okay, and is there new forms of matter in terms of very dense states? Now, this is Jefferson Lab today. There are 3 halls, poetically called Hall A, B, and C. Okay, and I'll go through this. This is the first accelerator. This is in his hand of Ernest Lawrence. Okay, and this is a little bit bigger. Now, but you know, this is recent, and then right now this is actually turned off, and we're going through an upgrade, and so there's $310 million provided to this lab for upgrading it from 6 GeV to 12 GeV, which will come online in about 3 years. Okay, and I'll talk more about that in a second. And so here's the lab. It's in Newport News, Virginia. This is where the Atlantic Fleet is located, right here. This is where the Merrimack and Monitor did battle, okay, a little few years beforehand. So there's a lot of history here. And here is Newport News Jefferson Lab. And so this is Hall A, B, and C. And this is the smallest hall, but good things come in small packages. And this is a 4 pi detector, more or less 4 pi. 80% of 4 pi, but better than 1% of 4 pi. Okay, so it surrounds the whole thing, and we have a set of wire chambers and such, and this is basically taking some of the wire chambers out, and you can see the innards right there. That's just the inner stuff. It's usually not in that state. Actually, there's nothing there now, because it's been all dismantled, and new stuff will be put in within the next year. So this is what this thing looks like. I'll talk about this. This is a scale of a human, so this is approximately, 4 human heights or 5 human heights. Approximately. So this is Jefferson Lab. What it has is it has 2 it's a race track. It has RF cavities here and here. So the electron goes in here, is accelerated, bent around, accelerated again, bent around, accelerated again. It can do this 5 times, and each time it can be switched into Hall A, B, or C. These can run simultaneously. This is Hall B, the hall that I work in. This uses cryogenic technology, and so superconducting the RF cavities are at 4K. The Q factor, if that means anything to you in terms of resonance, is on the order of 10 billion. So it's very, very precise. And so this is and this is what it looks like inside. And so this is the hall I'll be talking about, Hall B. Now, as I said, it's very poetic. Right here it's called CLAS, CEBAF Large Acceptance Spectrometer. And I should have this somewhere, but CEBAF stands for Continuous Electron Beam Accelerator Facility. Okay, Yeah, but I've been working there for over 20 years, so I'm kind of used to these acronyms. And so what we have here is we have a scale. We have basically, it's kind of like an onion shell, but we have 3 drift chambers, 1, 2, and 3, and they surround the whole thing. We have, and so they can measure charged particles. We have large angle calorimeters for measuring neutral particles like neutrons and gammas. We have coil superconducting, so if there's a magnetic field there, of about 1.5 Tesla meter, and time of flight counter so we can measure stuff. Let me just show a picture of this. And so here's a photon coming in, or an electron, and you can see that one thing is a K minus. So what happens is a K, it's set so the, is that a K minus. So look at the K plus right here, and so I have a gamma onto a deuteron, making a proton K plus, K minus, and something else. And so I have the magnetic field so that the positive particles are swept out like this. And it's a toroidal field, and so it doesn't have any sort of left or right. It just sweeps right out. So I can measure phi very well, and theta I do from reconstruction. And so I can see that I have this, and the time it takes to get from here to here, I have start counters and end counters that give time of flight, and I can particle identify quite well between a proton and a neutron. I did not change that. Okay, so right here you can see this thing, and it gives you an idea of electrons and protons, kind of a picture. So it's a toroidal B field. Oh, I said 5 Tesla here. It can change it. We can change the field. It can be up to 5 Tesla. 6 identical sectors. So like this, and this. Okay, 6 like a honeycomb. It ranges from 15 to 140 degrees, and phi is, we have coils in there, so we lose about 10 degrees in each sector. But we can measure pretty much, and our resolution is about 0.1% to 1%, which is pretty good. So I'll talk a little bit about this. So this is a CLAS detector right here. And so I have this big 4 pi detector surrounding this thing. Well, 80% of 4 pi. I can measure particles. And then somehow I have a photon beam that can come here and hit something and make stuff. But what if I want to prepare the photon beam in a very specific way? Let's say if I want to make it linearly polarized. Okay, and when I say linearly polarized, it means that the E vector is always in one plane, right? Either like this or like this. We do 2 different ways. We call this perpendicular, we call this parallel kinematics. So if I have a photon beam like that, well, to do this, I have to use coherent Bremsstrahlung. Bremsstrahlung, as you know, is German for braking radiation. And coherent, of course, means coherent. So it's a facility, and it's made of some things. I'll talk a little bit about this because I spent about many years of my life putting this together. And I'm happy to say it worked. And it was used for over 3 years or 4 years to do lots and lots of experiments. Now, beam time is $6,000 an hour. And a year is approximately 40 weeks of beam time. So if you multiply 60, I mean, that's a lot of dollars for this facility. Okay? Big number. More than you'll earn in your lifetime, at least me, okay? Maybe not, okay? And so we have a goniometer right here. We have a tagger. We have an active collimator. We have a paraspectrometer. All these things are basically mechanisms whereby I can make polarized photons. So let me talk a little bit about this. Why do you want to make polarized photons? Well, how do you start? I'm sorry, this was, I cut and paste. I know how to spell a line, but assume I spelled this correctly, or a line crystal. Okay. And so I aligned the crystal just right. So I put the crystal on a goniometer, and I said, well, first of all, I have to buy a goniometer to make linearly polarized photons. And so let me say, okay, I bought a goniometer. Here it is. Goniometer can put things precisely in space. It has pitch, yaw, roll degrees of freedom. It can move it up, left, and whichever way. So I have 6 degrees of freedom, and I put a target in one of these holders, and this is a diamond crystal right here. And so we have this right here, and we put a diamond crystal, which is approximately 50 microns, about half the thickness of a human hair, still not very thin, but thin enough. And we had to buy a bunch. And I'll tell you that in the diamond industry, you can't just say, I want perfect diamonds. What they say is that we'll cut you off a bunch. So we bought 10 of them, and 2 were good. And each one was $5,000. But when you're talking with De Beer just says, we'll give it to you, we'll try our best, but if it's no good, you still keep buying it. And that's the deal, because it's one group, you know, who control the diamond trade, and De Beer's it, and you do what they say. So we bought 10, 2 were good. And this basically says, this is a bad diamond because it's thick and funky, and this is thin, okay, and rolling curve. So we characterized this stuff in England at the Daresbury Accelerator, saying we had 2 good diamonds. One time I remember, someone from Scotland came and said, I have all these diamonds. I said, great. And I remember I stuck them on my desk at Jefferson Lab. I thought nothing of it. I said, what if someone heard I had diamonds in my desk and they stole it? It would be $50,000, but it's worth nothing to them, but it would destroy my experiment. So I went back and hid it in my office because I didn't want to take them home, but I hid them pretty well too. I couldn't find them ever again. No. And I'm richer. No, but anyway, we have an electron onto a radiator right here. I make a photon by Bremsstrahlung. You tag this right here, the post-electron right here, and we have a magnetic field. It causes it to curve, hits some of these hodoscopes. There are 384 of them. I know I put in each and every one when I was a postdoc, okay, and align them. 61 time encounters, basically back so we know the timing. They're 1/3 over, or 1/2 overlapping, or 1/3 overlapping is that, yeah, 1/3 overlapping, and so we essentially double the number of channels, and so we have approximately 768 energy bins. We go in an energy of the post-electron from 20% to 95%, so in a perfect world, the energy resolution is 0.1%. I will tell you that the energy resolution is about 0.15%, because there's some sagging and things like that.
What's a hodo?
Hodoscope is hodos comes from path, but a hodoscope is basically, oh, I'm sorry, it's like a Venetian blind sequence. And so I have,
What's the hodo?
hodo comes from path in Greek, but I only looked that up, but I don't know Greek, okay? Hodos, but it just means that you measure where the path came to. But you have basically all these, it's like a Venetian blind, and this is 10 meters long, and they're all little things along the thing. And so when electron comes in, it's going to curve down, hit one of these things. I know what the magnetic field is. I know what the charge of the electron is. I know what the speed is. It's going at the speed of light. And then I determine which one it hits. And then I determine this energy, and I know the incoming energy. Hence, the photon has been tagged. And the difference of these two tells me the photon energy to about 0.15%. Okay, 15 parts in 1,000 in the worst case. Now, this requires some explanation, and I'm going to do this. How do you know the diamond's aligned? Okay. Well, you take the diamond radiator, you more or less set it up. Let's see how much time I have. Okay, I'm probably not going to finish everything I have here, but I want to explain stuff. Okay, so I line it, I put it in a place, and then basically I have an electron beam come through, and then I have the normal like this, and I sweep it out a cone like that. And where the black lines are, it says I get a big flash. It's reverse color. And so then I can determine where I get the big flash, that's coherent, then I can set to be what energy I want it to be, okay, in space. And then we had to collimate this thing, that's my hand back when I was much younger. And so this is a 2 millimeter hole, so we had to get the center of the beam right through the hole because that's where the polarized photons are at the core, okay, to about 50 microradians, okay, 2 millimeters at 23 meters away. Big deal, but it's basically, we got polarizations of on the order of 90% at some points. That's the biggest in the world. Okay, so we have a very good polarized beam. Okay, so the details are, yeah, this is propaganda right here, but this is the whole thing right here. You'll be quizzed on this later. Okay, what's this distance? Yeah, etc. And so what we want to do is we're doing all this, so we want to look in this region. We want to take this from this. We want to determine these two mechanisms as I started. And so this right here is just scattering. This is the baryon resonances. And so I'm looking at the central region. So I'm using the central part of the detector to look at this. This is a lot of information, but there's different ways you can look at this. I can have an unpolarized beam, and I can see what happens. Sigma determines the cross-section. That's the likelihood of something happening. I can have a polarized beam coming in and see what happens, and I have a plane of polarization. I can have a circular I can have a target that's polarized. I can have a polarized beam on a polarized target. I can do all these things. It just takes money and engineering. But the idea is, remember, this is very complicated to extract this stuff, and so what I want to do is I want to use precision tools, polarized photon beams, polarized targets. I'm only going to talk about the polarized photon beams. Okay, but this later stuff, after this facility worked, people came in and said, well, what if I bring in a polarized target and take data? Yes, you can do that. We have, people said that's a great idea. What if I start polarizing neutrons and protons? Yeah, that's a great idea. Build it. And so this created a lot of different infrastructure at the lab.
Spin polarization you're talking about?
Yes. Yeah, longitudinally and transversely polarized targets. And so that gives you more information. And so what we have right here is we have a decay angular distribution. So I have a proton and omega coming out. Okay, so I have a photon coming in onto a proton, and then they're pushed forward. And so I have omega, which is a vector meson, and then that omega meson will decay immediately by the strong force in pi plus, pi minus, pi 0. I measure the pi plus and pi minus. I can't see the pi 0 because that decays immediately into 2 gammas. So I measure these things, and then I look at the angular distribution with respect to that plane. So I fixed a yardstick. I have something fixed in space, and I measure the angular distributions with respect to that. That's the reason we spent all this time building this, so that we could actually have precise experiments. And if the underlying baryon resonance has very different structures, it will have different angular distributions as expressed by the angular distributions of this, which will give rise to different spin parity states. Does that make sense? So I want to remember how busy that thing was, and I have everything overlapping. Well, different resonances will give rise to different particles decaying in different ways, and we want to measure that. This stuff has not been measured. Everything is new. This stuff has not been measured until recently. And so one thing we had is we had a circular polarized photon beam onto a longitudinally polarized target. That's called the E thing. You pull this out, you have these angular distributions, the function of cos theta. This is the asymmetry parameter called E. You can see this. These fits right here are the predictions from data, from phenomenological based databases. Because the data wasn't there, they didn't predict it very well. Okay, so it wasn't, so that it doesn't fit's not so bad. It just wasn't there. And so this data is new right here. And so what this says is that we were able to show new stuff. We're trying to understand the underlying structure by doing this data. Lately, we've done the following. We've noticed that we've taken K lambda decays, okay, and we see that the data is just doesn't, our data doesn't agree with this. We also see the following. This is from the PDG-12. Are you familiar with the particle data group booklet? Okay, so what we're doing is we put in a bunch of new states in that. And so you think it's big now. Wait till we're finished. We're adding lots of stuff. In fact, there's talk about taking out the baryon resonances altogether and making a new book out of that. Because we're compiling. Right now, there was nothing before. I mean, there was stuff beforehand, but we're like a little factory. We're just churning the stuff out and showing more and more stuff. And then ultimately, some smart guy like Feynman will come around and say, well, that's why. But we're trying to get the data, the encyclopedia out on this. And so this is the new data. Beforehand, it had not been seen, and these are the new states. The N1710, the N1880, et cetera, et cetera. And they're going to change the names, too, to make them a little more attractive, okay, because we realize that it's kind of ugly. Nobody can remember this stuff. And so that's one thing. So this is the big thing I just wanted to say, is that this is one of the useful things that are coming out. And there's big groups, such as Bonn and Gacino, Russia and Germany are analyzing this, and also groups in the United States, George Washington University. But this is one big thing that came out very recently. So what I said is, beforehand I was using photons. Well, photons have a q squared equals 0 point, right? And so real photons are kind of interesting, but that's kind of the start. What happens if I use electrons? They're going to exchange virtual photons. And there's going to be a momentum dependence or scale. Remember I talked in the very beginning that there's a thing called asymptotic freedom. Somebody asked me, you know, what happens when a quark gets close to another quark? Well, that's a good question, because the force changes. As you get really close to a quark, it becomes asymptotically free. It's very strange. And so the nature of the force depends on the distance that you're probing it. And so you can't do that with real photons, although it's a start. But now I want to understand, what is the nature of the coupling of the force of the quanta of virtual light with that of the parton? Does that make sense, kind of? It's kind of funny English, but I want to understand, what is the nature of probing the quark close and far away? And so what I'm going to do is I take an electron right here, it scatters, I have a photon come in here, and then it makes this in some way, and then I talk about different amplitudes excited. What that means is different means of how close you are to it. And then I look at the things that decay. This is a little bit complicated, but I'm just going to go through and explain this in a little bit more clear English. Okay, so here's this picture again. I like it. Okay, so I'm going to say now with really close, what happens? So actually, it's a mess. I didn't want to show this in the beginning, but this is what a proton looks like. Okay, you got these three quarks, you got these effervescent quark-antiquark pairs here and here. Sometimes the antiquark-quark pair is a strange anti-strange quark. It's very bizarre. Okay, that's just another quark. And there's strangeness content of protons. People are looking at that. Then I have all these little loops right here. These are gluonic fields. There's 8 of them. Okay, there's 8 different types. And the thing is, let me ask you, do photons couple with photons? When I'm looking at you, is there photons interacting with other photons? No way, because it'd be black, right? And you can see me, unfortunately. So the thing is, photons don't couple with photons. Gluons couple with gluons. So gluons couple with quarks. Quarks couple with quarks. So you have a lot of stuff going on inside. And so now I have to understand what is the nature of the mass of the proton. And if I say I just have 3 quarks, use a Lie algebra, basically I've said something that's kind of sort of true, but it's more cartoonish than reality. So now, but it wasn't until recent that you could really do this. You have to have a 4-pi detector, you have to have linearly polarized photons, you have to have longitudinally polarized electrons, you have to go through all this stuff, and then you have to start coming with models to understand this. Again, this is a model. So you want to, gluons can couple with themselves and turn from blue to green. Okay, they're called blue, green, or red. They can't violate the overall color neutrality, and the strength of force depends on the separation of different quark colors within the nucleon. Okay, and I stole this boldly from the core of matter, the fuel of stars. Okay, so this is one thing right here. Basically, this is QED. This is the metric right here, Q squared is Q mu Q mu. It's a form of momentum transfer squared carried by the photon. That's an invariant. I'm going to talk about Q squared. That's basically this for momentum that's transferred. I use that because it's the same in all frames and easy to calculate, or easier. And the bigger the forward momentum transfer, the smaller the distance probe. So you can use the Heisenberg uncertainty principle to give you an idea of this. And so delta K is a measure of delta D. Okay? So the momentum transferred, so where the electron goes, tells me how close it was to a quark. Okay? And so I use this to say, how close was I to that quark, and what is the coupling at that point? Now I know there are quarks in there, but am I interacting with gluonic fields? Am I interacting with quark-antiquark pairs? Or am I really far away and interacting with the pionic cloud around a proton? I mean, there are different ways of looking at this, different degrees of freedom. It is really a very interesting problem because there are many ways of looking at it. And every scale has a different way of looking at it. So what I want to do is I look at this as a function of Q squared right here. And I notice that if I scale by Q squared, I get some sort of flatness right here, really far away. And so what I want to do is I want to look right here. And this is my fancy graphics. I actually drew this myself. Okay, so this is a magnifying glass, and I want to look at this region. And these are different types. This is the 1440. That's the Roper. It has a name. Okay. And this is D13. It doesn't have a name, so we call it D13, and the S11 1535. Okay, so these are different states. So this is what I want to say. I said hadron structure with electromagnetic probes. Is it basically just some nucleus or nucleon with a bunch of pions around there? Okay. I mean, basically, the old model was if you had a proton and a neutron, it was pion exchange, Yukawa potential. I'm sure you've seen that. Okay, that's one way to look at it. It is a completely correct way to look at it at that scale. But if I look closer, I got 3 quarks. If I look closer still, I got perturbative QCD, which means that it's very, very, and I have gluonic fields and stuff. And so what I can do is, what is the degrees of freedom at varying distance scales? When someone asks me, what's the nature of the force, I try not to be difficult answering that. I said, I don't know, your question's not precise enough. At what scale? Please tell me at what scale. Then I can answer your question. But otherwise, I'm just going to talk a lot and not make any sense. And so here I have, this is from lattice QCD calculations, and this is Dychen's finger. This is not data. These are two different theories. And basically it looks at the nature of Q of a given quark as a function of its mass. And so what I'm trying to do fundamentally with this set of experiments that will take place in 5 years from now, 4 years from now, is understand what is the nature of mass inside as a function of scale. Okay? And so everybody talks about the Higgs boson. That's cool, that's interesting, that's nice. But most of the mass comes from a proton, because most of regular mass, not talking about dark matter, comes from protons and neutrons. And yet, what is the measure of mass as you get closer and closer to a quark? And so what I do here is, this is a fancy graphic, so hold on to your seats, right there. Okay? So again, right here. So as I go this way, I'm measuring down here. So as I go closer and closer, I'm measuring the nature of the exchange of forces. Okay? That's the idea, at the scale. I hope that makes sense. Okay, so insight to the structure. So what I want to say again, the active degrees of freedom and Baryon structure at various distance scales, the 6GEF program, which just finished in May of 2012, offered detailed information, but we're still studying this stuff. We have lots of data in the can on the transition of n-star structure from meson baryon to quark degrees of freedom. So looking at the pion cloud to the quarks inside, and then we have a quark core regime, and then we have other stuff out here. And so we want to determine what is the nature of the structure as a function of scale. And so actually I like this statement. He's a very highly respected theorist in my field, and he says the strongest things. I won't say this, but I'll quote him. Okay. There is no greater challenge in the standard model and few in physics than learning to understand the truly non-perturbative long-range behavior of the strong interaction. Okay, almost poetry. Very strong statement, okay? Now, what I want to do is I want to study this scattering of electron with a virtual photon onto some proton, and then I want to extract these these matrix elements. And so what they do right here is basically these are the transverse matrix elements, and this is the longitudinal. Remember when you do Feynman diagrams, the physics is in the matrix elements. And so I want to extract the matrix elements and get the physics. And this stuff right here is my E&M probe. So I'm using an E&M probe, go from one state to another state, and I'm extracting these transition amplitudes. This is funky words, funny words, but it just means their behavior, these matrix elements. I want to extract that right here. And so that basically tells me. Now here, I don't want to talk too much about this. I just want to say, notice this line right here and notice this line right there. If you don't incorporate the meson cloud effect at low Q, you can't reproduce the data. So it's a reality at close distance. You must have a pionic cloud. So when I say degrees of freedom depend upon distance, you must take into account that there are pionic clouds. Protons and neutrons would never form without a pionic exchange. It's a reality. But when I want to look inside the proton, I don't care about what's outside. I mean, that's way out there. I don't care anymore. So now I basically don't have to worry about that anymore. Okay? But it's a reality. And then basically we show this. This is data. This is all new. And the thing I want to say is that this basically is from different channels. So this is the 1 pion channel. This is a 2 pion channel data. And notice they agree. And what we're doing is we're extracting these things. And that we see a crossover right here. The Roper resonance, the P11-1440, used to be the biggest conundrum in this thing. Of course, it never made the New York Times front page and stuff like that. But nobody could understand. They do this Lie algebras. They say, this makes sense. And then there's the Roper. And always I went to so many talks, and then there's the Roper. And so it was given a name, the Roper, named after the guy who predicted it, Mr. Roper, Dr. Roper. And then finally, recently, in 2012, made these measurements, took this out and says, oh my gosh, it crosses the axis. It's consistent, and people says, with a radial excitation. So of course it didn't fit our Lie algebras because we don't have that degree of freedom. We have orbital, but we don't have breathing. Okay? So it says there's richness in this. And so people can understand this. And so talks about radial excitation, etc. And then we look at the D13, and we pull this out to show you, and you can see it scales out there. So there's a lot going on. So the nature of the exchange of the forces, as expressed by these A1 half, S1 half, A3 halves. I mean, this is kind of hard to see, but just basically I'm just saying the nature of the force exchange depends upon the distance. That's the take-home message. The scale is important. So when you ask somebody what's the nature of the force, someone's always going to say, what distance? Okay? Are you talking about, neutron way far away? Yeah, there's a pion cloud. I get really close, there's quarks. If I get really super close, well, they're asymptotic free, and I've penetrated the gluonic field. So I have a few minutes left, and I'm going to finish up on time. So there's a 12 GeV upgrade. They're going to add a new Hall. They're going to use linearly polarized photons in this Hall. Okay, as we proved in Hall B that it worked so well for 3-4 years. They're going to add another arc. The technology has gotten so good. This was the first lab to use cryo modules for RF. Okay, and they took a big chance to do that. It worked. Now I'll tell you one thing. I was there in 2003, September 2003, there's a thing called Isabel coming. I was on sabbatical. Isabel was a big hurricane about the size of South Carolina. I saw it, and the eye was about, really big. And so I saw it coming towards coming towards North Carolina, or actually towards Virginia. Well, I bravely got in my car and went over the Appalachians to Kentucky. Okay? Because I know that a big hurricane can take trees and fling them through the air, and there's no ninja move I can use to get me out of that. And so I know that if I'm far away, it can't hurt me. So I came back, and I didn't have water for about 2 weeks, 3 weeks, but it was still warm there. But the thing was, it took out all the electricity, so all these things came up to room temperature. And it took about 8 months. And at that point, everybody just did the following. They just said, let's repair all the bad modules that we have. Now, we brought it to room temperature. And so then they repaired it, got it to work slightly better than before. And then that was in 2003. Now, what's happening right now is they're replacing with 5 new cryo modules. Their Q factor is much better than before because people can build them better. And so we're going to go from 6 GeV to 12 GeV and add 1 Hall. That's going to be about $310 million, not including the NSF grants and DOE grants to the private investigators. Could I speak any faster? Okay. Now, here's what it's going to look like right here. The design has changed. But remember, this is still 4 pi, but we're at higher energy, so everything's thrown forward more, okay, in a relativistic way. Here's a picture. This is at ISU. We're building, or have built, Region 1. And so we have finished all 6 for the wire chambers. Each wire chamber is about as tall as I am high and as wide as I am tall. So it forms like, or it's an equilateral triangle that each side is about 6 foot long. And so we've strung all of those things, and we're going to take them to Virginia in April. So we're just storing right now. We were going to take them earlier, but the government shut down. So we were going to take them 3 weeks ago, but we thought that it's kind of hard with the government not open to deliver something to the government, right? No, that had a real impact. I mean, we're going to take this on a piano truck. Okay, there's fine art you can take from Chicago to San Francisco that have nice, comfy beds inside, basically shock absorbed. They can take antiques, and so we're going to use the same thing. So we have all that set up and everything. We said, can't do it because the government shut down. Well, okay, it's funny. But anyway, here's some people working there, and this is what we're doing. So we're the furthest group west of the Mississippi, furthest group west, and we're the biggest group west of Mississippi. There's 5 professors associated with Jefferson Lab physics. We got this approved in 2009 for experiments to take place in 2017. These are the people. I'm one of the spokespersons on this. Okay. This is ridiculously difficult to write one of these things, but we got 40 days of beam time. It's going to be about $7,000, $8,000 an hour, something like that to run 1 Hall. You multiply that by 4, that tells you roughly $23,000 to $25,000 an hour. Okay, and we get 40 days. So that's pretty cool. And you have to go through lots of review and such. So we have 40 days. Electromagnetic excitation of stars using electrons. It has 2 major components. We're going to look at the nature of the force as a function of distance, transition helicity amplitudes, and the spectroscopy, what's there and what's not there. And so this is basically done in conjunction with theory groups right here. There's a lot of words here, but and we're going to use lots of different channels to look at this. So we have a 4-pi detector building. Part of it will be transported from Idaho to Virginia shortly. And then this is the big message right here. We're going to look at this as a function of distance at the nature of the coupling and get an idea of the mass. So this is what we're going to fill in right here. We're going to look at this region and see how this looks. So we're going to try to look at this, and if it might look different. Who knows? I mean, this is just projected and what it might look like. But you never know until you measure it, right? And so we need theorists to look at this and a lot of help with this, and it's a very important problem because no more than 98% of the n-star mass is generated non-perturbatively. So how does this generate it? And one thing I wanted to say is that we just published a big, big paper for your reading pleasure, and if you have insomnia, there's 100, well, it says 99 pages, it's actually 120 pages, okay? And that 27 people were involved, 5 experimentalists. We form working groups to discuss this, and it's basically everything we know about baryon resonances and what models and such. And so we worked on that, and I worked on this too. First chapter probably is understandable, okay? But it's actually, well, it was a lot of hard work, and not because I don't know if you'd want to read it because it was hard work, but it basically is the state of knowledge of baryon resonances, put together by 26 of my best friends. Okay, so thank you very much.
Time for a few questions, please.
It'd be nice if some of those resonances were a little sharper. Why are they so broad? Or did you explain that to us?
No, I did not explain that to you. It's the nature of how things, I mean,
Is that lifetime? Or?
that's basically what you have is a Bright-Wigner distribution, and the width is usually in terms of the delta E, delta T, and so the uncertainty in time, so it populates a certain phase space. So the width has to do with the uncertainty and energy as expressed by the uncertainty in time, which has to be greater than or equal to h bar over 2.
Yeah, right.
And so therefore the time is on the order of 10 to the minus 24 seconds plus or minus a little bit. So there's some phase space it can go into.
So it's a messy, okay.
Yeah, it's messy.
Messy,
Yeah,
yeah.
They're
bumping into each other all over the
it's a fascinating problem. It's probably will engage me all my professional career, and I probably wouldn't. I picked this topic not realizing how hard it is. But the more you study it, the more you don't know, and the more you want to study it, and yet it's messy and hard. But you know, it's fun. But the thing is, what makes a proton a proton? And all these things bumping in another. So you can resonate a quark in a certain way. It has a breathing mode, or it has some sort of spin flip, or it has some sort of oscillation, or what have you.
I was happy with the statement that it's just 3 quarks. That was me.
So was I. But the thing is, unfortunately, data does not support that statement.
Well, you look too close.
So you've talked about baryons states made out of 3 quarks, but you could also make one with 3 quarks plus a gluon.
Yeah.
Kind of a valence particle. And I suppose you're looking for them.
Yeah, actually, I did show on that table, I cited Dudek and Edwards, and basically what it says is that there's hybrid models, and so there can be quark, I didn't even go and touch that, okay, because that's yet another complication. So it's even...
How would you know when you see one?
Geez. The back of the envelope answer is then I would say if it's consistent, well, yes, that's a good question. Okay, no, I mean I can give an answer, but the thing is, it depends upon what you're looking for and how the angular distributions are. And then what you have to do is you have to do several things. You have to use polarized targets, polarized beams, and then see if that's consistent, you know, with one state. And then that's basically the steam shovel approach. And then you take the trowel to dust and brush, and then you start using the photon, the electron beam to see how the helicity amplitudes change. And if they act in a way that's not consistent with fermions, then you have that. But there's a lot of stuff in there, so that's I can't. And then I may have forgotten something. Is that a fair answer?
As good as any I've heard.
So it's an I don't know, but I'm really interested, and I'm going to look deeply into this because there's details. There are details.
Aaron.
So, you mentioned that there's a controversy between the sides. Could this just, the two different experiments or whatever are saying that there's two different sizes of the proton is whatever. Could it be that the two different experiments are just preferentially probing a different way, whether it's the symmetric model or the dichroic model?
No, I don't think so. Let me just tell you what I know. There's been recent work from Germany, and it's been published in Science and Nature, and they've been using muonic atoms. Now, a muon has an orbital a muon is 207 times that of an electron, and the Bohr radius scales as it gets that much smaller. And so there's a big likelihood for the muon to be inside the proton. Electron, if you do the calculation, it's less than 1 part in 1,000 or something like that. For a muon, it's sizable. It's like about several percent. I believe. I'm not an expert in this, but that's what I've read. And so from these very precise experiments, and they reproduce the Rydberg constant, which is a very well-known constant to 1 part in a zillion. Okay, you can look at that. Zillion's not the right name, but 1 part. And so it's the most precise thing. So they get all that stuff right, and so you could say, why are they wrong? And nobody can find a reason. They say it's 0.84. Yet there's about 15 elastic scattering experiments with electrons that says it's 0.88. And they all, the elastic scattering experiments agree with each other within very small error bars. And then you have, on the scale, then you have this. And you can't find anything wrong with the muonic atom experiment, so it's a conundrum. And so people say, well, everybody wants to remeasure this stuff with other means. So something as fundamental as the size of the proton is not known precisely.
So there's no structure in the muon?
No. Electrons have no structure that we know of. That's a weird statement, I know. But I know. That really bothered me, and since I don't think about that anymore. But the thing is, as far as I know, it's consistent to say that there's no size to an electron or a muon.
But somebody has the radius of the electron.
No, there's no such thing.
Wait, read it in books.
No.
Yeah, but there is an electron radius.
No.
Classical.
That's classical radius.
No, I can stand corrected by people who know more than I do, but as far as I know, it's consistent with everything. There is no size to a lepton. Now, this is weird, but what is the size of a quark? I don't know. It has no size. There's no preons. These fundamental particles, I don't know what they are, but they don't have spatial extent as been measured with anything. So if they do have size, they're really, 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 really small. But I don't, perhaps someone can answer that better. I don't, they have no size as far as I know.
One more question.
Yeah. You have mentioned 3 possible levels for the proton structure. One is the meson cloud.
Yeah.
The second one is they may call the constituent quarks. Then we have the perturbative QCD.
Yes.
So in the older literature, there were terms such as the constituent quarks or current quarks. Current quarks refer to the perturbative QCD mass very small.
Yes.
But however, for the constituent quarks, they are heavy.
Yeah.
It's about 1/3 of the proton mass and so on. My question here is the following. Now I want to know the status, both theoretically and experimentally, whether now we can make sense of reserve the structure of the constituent quarks in terms of the current quarks and the gluons or not.
I'm going to answer this in a strange way, and I asked Nathan Isger something very similar to that, many years ago. Now, he died over 10 years ago, but he was the chief scientist, and he was really a nice guy because he would talk to people, and I don't know, you knew him, yeah. So you could ask him anything, and he didn't think the worst of you. And I said, but the thing was, he says, pick your degrees of freedom and pick them very carefully. Now, he didn't say this, but you can look at the constituent quark model as being somewhat naive. It's just some sort of way of looking at a Lie algebra, and then you have to add in terms. But I think the reality is more like this. But the nature is, what is a coupling? When you cloak a quark with a bunch of gluons, then it changes its mass, or the nature of the exchange of force. Is that? And so, is there such a thing as a constituent quark? Maybe far away, but I think it's more of a method for calculating instead of a reality.
There's a mathematical model. I think now it still works good.
Yeah, it does. It does at some levels, and then it fails in other areas. But for example, Santopinto and I'm forgetting his name right now in Italy at Genoa. They work on the constituent quarks, and so they wouldn't like what I just said. So, but what we did in this paper, and I just to tell you, we got just I'm not trying to advertise this too much, but we got everybody we knew in the business, and not everybody agrees with one another. And oh, geez, I'm going the wrong way. Just give me a second, please. I'll be there in a second. Okay, so faster. Come on. Okay, I'm glad you're very patient people. Okay, one more second at a relativistic speed. Okay. So, yeah, almost there. Wow. Okay. So of course I lost it, but if I go down here one more time, if you bear with me, I spent so much time trying to find it, so let me try to find it one more time. So here it is, right here, and I can use this. So this paper right here. Now Giannini, I couldn't remember his name. He does constituent quarks. Okay, and Santopinto, she does constituent quarks. They're at Genoa. And then you have other people such as Lee, who does more phenomenology, and so we have all these groups, some people doing lattice QCD. So the nature of what a quark is defined differently in different models. But some people say that there are 3 quarks, and you can say it's constituent. Other people say that's far too simplistic of an idea. There's always cloaking of gluonic fields. And so what we did in this paper is trying to say, we don't have an answer, but this basically is, this is a state of knowledge, and these are the models, and this is their agreement, and they make different predictions, and some have effective Lagrangians. You see what I'm saying? And so you're asking me to say what is the truth. I'm saying there might be different truths.
But are there some attempts?
Oh, yeah.
Experiments try to resolve, such confusions or
Yeah, and the thing is, there's coupled channel analysis, because basically people think they haven't really measured things very well, and how do you put on the channels, because things can decay in different ways and interact at the amplitude level. I know I'm not answering the question. You want me to say yes or no, and I'm not going to do that. Okay, but I'm saying that I'm not trying to be a lawyer. I'm a scientist, and so the thing is, it's. Now, if Mr. Let's see, I was talking about Roberts, Craig Roberts. Now, he has strong opinions. I quoted him. He'd say something, and he'd strongly support it. He would say, there is no such thing as a constituent quark. I won't say that.
Okay, well, thank you all for coming. Interested in going to dinner with Jen and Very nice.
Well, thank you.
Cool. I actually learned quite a bit.
Yeah, it's been working on it.